Hello friends, this video on coordination compound part 14 is brought to you by examfear.com. No more fear from exam. Try to find a figure, shape of COF6. So if you see the oxidation number of cobalt is +3. Same concept here. So cobalt +3, the way we have done just now, will have how many electrons? Same thing. It will be 3d6. Okay, so let us draw this value. 1, 2, 3, 3d, 4s, 4b. Okay, 4d also. If you want, you can draw. If you want, you can ignore also. So 3d6, 1, 2, 3, 4, 5. And then 6. So if you see here, again, they have 4 unpaired electron and 1 paired, with 2 paired electrons. Okay. Now, experimentally, that it is seen that this particular compound is paramagnetic. Okay, paramagnetic. This is experimental. Since this is paramagnetic, it will not move the electrons. Okay, so now we need to bond with 6 fluorine molecules. 1, 2, 3, 4, 5, 6. We need 6. Why? Because each of these fluorine molecules will come with 2 electrons. So this is the hybridization. What is the hybridization? sp3d2. Right? S3p into d. sp3d2 is this guy. This is also octahedral. But I can see that this is octahedral in shape. This is octahedral. So the final thing will be, you want to draw 3D, 1, 2, 1, 2, 3, 4, and then it is sp3d2, 1, 2, 3, 4, 5, 6. So each of these will have pair of electron because each of the fluorine comes with a pair of electron. This will be the final structure, and if you see in this case, it is paramagnetic. It has unpaired electron, and this is called outer orbital. This is called outer orbital complex. Why? Because in this, if you see, the outer d orbital is used for bonding. The inner d orbital could not be used. The outer d orbital is used for bonding. Okay, also called high spin complex, because this kind of compound has high spin. The spin is not nullified. If this electron moves, then this spin would have nullified, but experimental data say this is how it is. So this just explains, based on experimental data, it explains the structure, why it is like this. Okay. So let's see this NiCl4, 2 minus. Let's try to draw the structure. Oxidation state of nickel will be +2 here, and nickel 2 plus electronic configuration is argon 3d8. Okay, so argon 3d8, let's draw 3d. 1, 2, 1, 2, 3, 4, 5, 6, 7, 8. This is how it is. Then this is 3d, and it is 4s, 4p, 4d. Okay. Now if you see, it has been seen experimentally that this particular compound is paramagnetic. For this to be paramagnetic, it should have unpaired electron. That means we will not move these electrons here. So now it needs 4 orbitals to pair. 1, 2, 3, 4. So this guy will hybridize to form sp3 hybridization. What you will get here is 3d sp3. So sp3 all will be filled with 2 electrons, and here if you see what will happen is this is what will happen. So here if you see sp3 hybridization is tetrahedral, so this shape will be tetrahedral, and this is paramagnetic. So it is paramagnetic. Actually this was seen experimentally, and with that this conclusion was drawn. Okay, Let's say another nickel coordination compound NiCN42 minus. Here the oxidation state is +2. Same thing, Ni2 plus. Write the electronic configuration. It is argon 3d8. So let's do this. 1, 2, 3, 4, 5, 6, 7, 8. 3d 8, and you will have 4s orbital, 4p orbital or empty. Okay. Now this particular compound, experimentally it is seen that it is dimagnetic. That means we have to rearrange this electron from here to here. Okay. So once we do that, what happens is, this is how my 3d orbital is. And then you have 4s, and you have 4p. Okay, it needs 4 orbital because the coordination number is 4. 1, 2, 3, 4. That means these bonds will happen. That is dsp2. So dsp2 is square planar. So this explains why this is square planar. Actually, this is square planar. This is square planar. Explains why it is square planar, and also dimagnetic. Again, it is experimental data. Okay. Please note this hybrid orbital doesn't exist. Actually, this is just understanding to explain the concepts easily. It is actually mathematical wave function. The whole orbital is mathematical wave function in the atomic world. Thus, understanding to understand things a little easier. So let's try the other one, CrH2O6 3+. So here chromium 3 plus is the oxidation state. You will see the chromium 3 plus is argon 3d. So if you draw the shape 1, 2, 3, 3d, then you have 4s, then you have 4p. Okay. Now it is seen that this is paramagnetic. This is seen experimentally, it is paramagnetic. That means pairing will not happen. Pairing will not happen. Again, we'll talk about the next theory where you don't need this experimental data. Here in this valence bond theory, we are a little bit relying on this experimental data, but in the next theory that doesn't need the experimental data. We'll see that. So that means there is no reorganization of electrons, and thus there are 6 electrons. The coordination number is 6. We need 6 orbitals. 1, 2, 3, 4, 5, 6. That is D2sp3. Okay. D2sp3 is what? Octahedral. That means the shape is octahedral and it is paramagnetic. Okay. We'll take few more to understand this concept. FeCN6 4 minus. Again, the oxidation state is +2 for this because Cn each is -1. So -1 into 6 minus 6. Minus 6. This has to be +2, so that total charge is -4. So here, if you talk about the iron +2 oxidation state electronic configuration, is argon 3d6. Let's draw this argon 3d6. This is 3d6. 1, 2, 3, 4, 5, and 6. Correct? This is there. Now it is seen experimentally, and let's draw 3d. We'll have 4s, then we'll have 4p. Experimentally, it is seen that it is dimagnetic. That means pairing has to happen. So some pairing will happen. One electron will move here, other electron will move here. So after reorg, what will happen is you will get something like this: 1, 2, 3, 4, 5, 6. And then you have 4s. Now coordination number is 6. You need 6 orbitals. 1, 2, 3, 4, 5, 6. Because each ligand will come with 2 electrons, and 2 electrons need 1 orbital. So you need 6 orbitals. There means you need these orbitals. That means you need D2, 2 of D orbitals, 1s and 3p. D2sp3 is the hybridization. D2sp3 is octahedral. That means it is octahedral. Right? So actual, if you see the shape will be like this. It will be 3D. Okay. then it will be D2sp3, and each of these will be. So with this you can actually say that it is dimagnetic because no unpaired electron, okay, and it is octahedral based on this chart. Okay, the next is FeCl4 minus. So here iron will be +3 charge. So Fe3 plus is what? Argon 3d5. So let's draw the 3d5. 1, 2, 3, 4, 5. 4s. 4p. Now experimentally it is seen that this is paramagnetic. If it is paramagnetic, that means the pairing should not happen. So that means nothing will happen. We need 4 orbital, 4 coordination number 1, 2, 3, 4. That means sp3 hybridization. sp3 hybridization is tetrahedral. Thus its shape will be tetrahedral and it will be paramagnetic. Okay. Actually shape will come something like this. 3D. It will be sp3 hybridized. All these orbitals will be completely filled, but these are unpaired electrons, so it is paramagnetic. Okay. So the magnetic property, as I told, we use that as a data to write the structure, and this is measured by a magnetic susceptibility experiment. Okay, and this result is actually used to get the information on the structure and the metal complex. We have used that. Based on the metal experimental data, we give the structure. For example, we experimentally it is saying that MnCN6 3 minus, it has 2 unpaired electrons. This is experimental. And MnCl6 3 minus has 4 unpaired electrons. So there is a difference. I mean, it's all experimental data, and with this data we actually draw the picture. For example, also FeCN6 3 minus has 1 unpaired electron, and FeF6 or FeCl6, let's say 3 minus has 5 unpaired electrons. These data is actually used to draw the structure. Okay, so magnetic valence bond theory uses the data to explain why it is paramagnetic, why it is dimagnetic, using the concept of inner orbital entities and outer orbital entities, outer orbital complex and inner orbital complex. Okay, so we'll take some more numerical now. So spin only magnetic moment of MnBr4 minus is given. We have to predict the geometry of this complex. Let's see magnetic moment is what? Mu is equal to root of n into n plus 2. That is value is given is 5.9. Okay, 5.9. Okay, you square both sides, so you get n into n plus 2 is almost 36. Okay, and almost 35 actually. And this is nothing but you put 5 into 5 plus 2, that is 7 into 5, 35. So with that directly you can say n is equal to 5. You can do maths, or you can do 1 by 1, n is equal to 1, you put the value, n is equal to 2, you put the value, get this. Or directly if you have solved so many questions, you can actually do it fast. N is equal to 5. That means n, or I can write n is equal to 5 given. 5 unpaired electron. Unpaired electron. And let's explain the geometry of this now. Okay. MnBr4 minus 2. Mn has the plus 2 oxidation state. Mn plus 2 oxidation state is what? argon 3d5. Put the value 1, 2, 3, 4, 5. This is 3d, and this is 4s, this is 4p. Okay, now experiment says n is equal to 5, that means you don't need to touch this unpaired electron. Now your coordination number is 4, that means you need 4 orbitals 1, 2, 3, 4. You use this to form sp3. Why sp3? 1s and 3p. sp3 hybridized. sp3 hybridized is tetrahedral, that means you can say that the geometry of this is tetrahedral. Okay. Using experimental data, we could actually say what is the geometry of this particular complex if we know the valence bond theory. Thank you. Visit examfear.com to watch more videos, attempt free online tests, get free study materials, find tutors and mentors, and much more. Thanks once again.